Welcome back to the Explainer. Today, we're looking at the absolute backbone of great software architecture in Python, object-oriented programming. If you've ever stared down a massive, overwhelming wall of code and thought, there has to be a better way, well, you are in exactly the right place. Okay, let's dive into this. How do you keep large Python programs from just falling apart? Have you ever tried to build something complex, only to have it completely collapse under its own weight? Yeah, in programming, we call that spaghetti code. It's tangled, it's messy, but the solution? Object-oriented programming, or OOP. It is literally our structural savior, transforming all that chaos into organized, manageable systems. So here is our architectural roadmap for this explainer. First, we'll look at the OOP blueprint. Then, we lay down the foundation with classes and objects. After that, we're scaling up with inheritance, customizing with method overriding, and finally, we'll wrap up with simplification through abstraction. Let's kick things off with part 1, the OOP blueprint and solving that dreaded spaghetti code problem. Our main goal here is pretty straightforward. We want to summarize and apply the basic concepts of OOP to make our code highly reusable and, honestly, just a lot easier to work with when programs get large. We're moving away from those messy, linear scripts and stepping into the world of clean, maintainable systems where every single piece has a distinct purpose. To pull this off, we've got a 4-step mission ahead of us. Step 1, which we'll call Task 6, is to build a class. Step 2, Task 7, is to inherit properties. Step 3, Task 8, is to override methods. And our final step, Task 9, is to implement abstraction. Every single one of these steps logically builds right on top of the previous one. So let's roll up our sleeves and get our hands dirty. Moving right along into Section 2, Foundation, Classes and Objects. This is where we lay the groundwork for your program. So the crucial point here is understanding exactly what a class actually is. By definition, it's a foundational blueprint where we declare our member variables and initialize them using things called constructors. Think of a class like an architectural drawing. It's not the house itself, right? But it tells you exactly where the doors, the windows, and the walls are going to go when you actually build the object. For our first mission, Task 6, we've got a checklist to help us lay this foundation. We need to create the class itself, add in our member variables, build out our methods, which, by the way, are just functions that live inside the class, and add our constructors to initialize everything. But the real secret sauce here is the self variable. The self variable allows you to access the members of the class right from within the class itself. It's the glue that ties all these foundational pieces together inside our blueprint. All right, on to Section 3, Scaling Up with Inheritance. This is where we start reusing code like a pro. Inheritance is this brilliant concept used to achieve code reusability. It completely solves the massive headache of code maintainability. Think about it. Instead of writing the exact same code over and over again, which is a total nightmare to update later, we can simply inherit properties from existing code. By not repeating ourselves, our programs become incredibly efficient and way less prone to bugs. Now, what's really interesting here is the sheer variety of ways we can structure this inheritance. We aren't stuck with just one single method. You've got single inheritance, multiple inheritance, where a child actually has more than one parent, multi-level inheritance, which you can think of like a family tree going from grandparents to children, and finally, hierarchical inheritance. Oh, and remember those constructors we just talked about? They play a huge role here in dictating how data and initial states get passed down through these different family trees. Task 7 asks us to literally put this into practice. We're tasked with creating a child class that inherits properties directly from that parent class we built back in Task 6. This is where you really see that promised code reusability jump into action. You're getting all the variables and methods of the parent completely for free right inside the child class. Next up is Section 4, Customizing with Method Overriding. Let's look at tailoring your modules. And this brilliantly illustrates how we apply method overriding to implement and integrate our modules. For Task 8, we basically create the exact same functions in both the parent class and the child class. By doing this, the child class function overrides or replaces the behavior of the parent class function. It's fantastic because it lets us keep the same predictable interface, like the same function name, but we get to customize the actual behavior specifically for that child class. While we're on the topic of customization, it is definitely worth highlighting operator overloading. Just like we can override methods, operator overloading lets us give extended, custom meaning to standard operators. Think of your standard plus or minus signs, beyond their predefined operational meaning. It's just another incredibly powerful trick to keep in your OOP toolkit. Bringing us to our final section, Section 5, Simplification through Abstraction, or as I like to call it, hiding the wiring. So abstraction is a technique to identify and use simplification by intentionally hiding complex implementation details. Think of it exactly like a light switch in your house. When you walk into a room and flip a switch, the light turns on. You don't need to see the electrical wiring in the walls. You don't need to understand the local power grid, and you definitely don't need to know how the circuit breaker works. All those complex implementation details, they're completely hidden from you. You just interact with a simple, abstracted interface. Cask9 brings our mission to a close by having us essentially build this light switch. The workflow here is to create an abstract class and add abstract methods to it. Now, an abstract method is basically a rule. It says, hey, any child class must have this specific function, but I'm not going to tell you how to actually write it. Then, we implement those required methods in the child class we created back in Task 7. We're enforcing a strict structure at the top level, but leaving the specific, kind of messy implementation details down at the bottom level with the child classes. Before we completely wrap up, let's look at two self-learning principles that are absolute hallmarks of truly professional software design. The first is the Single Responsibility Principle, or SRP. This principle states that a class should have one and only one reason to change, meaning every single class should have just one specific job. If you've got a class trying to handle user logins, saving to a database, and sending out email notifications all at once, it's doing way too much. Breaking it down keeps your architecture perfectly organized. The second topic here is the Open/Closed Principle, or OCP. This means your software entities, like your classes, should be open for extension but completely closed for modification. In other words, you should be able to add new functionality, say by using inheritance to extend a class, without ever having to go back and alter the existing tested and stable code. It ensures that as your program inevitably grows, you aren't accidentally breaking the foundation you worked so hard to build. Wow, we have covered a massive amount of ground today. We've mapped out everything from the foundational basics of classes, the self-variable and constructors, all the way through the complexities of inheritance, method overriding, and the sheer elegance of abstraction. You now have the complete OOP blueprint right in front of you. The principles are clear, the tasks are laid out, so the only question left is, how will you use these tools to simplify your next big Python program? Thank you so much for joining me for this explainer, and happy coding.